Welcome to our discussion on everyday geometry and applications. We've got a few objectives that we want to look at in this video. Let's dive right in. So geometry is one of those topics that we see all the time. We need to use it when we're building houses and buildings and roads, right? It comes up in geometry, art, music, all over the place. So it's one of those studies that is often misunderstood by students. They think of it as just a big long list of formulas to be memorized, and they never see the application of it to the real world. So hopefully some of these examples will show you just how useful geometry can be. All right, before we jump into those, let's make sure we get some vocabulary out of the way. We all are speaking the same language, right? We know that a point is just a dot in space. A line is basically a collection of points, and we can always designate any line by just finding 2 points, right? The rule is any line is determined by 2 points. Whenever you see this little double arrowed symbol above 2 capital letters, that denotes a line, and we call it AB because it goes through the points AB. Of course, we could call it CD, XY. We could use any letters we want. Then we have rays and line segments, right? Line segments are ones that start and stop on both ends, right? A regular line goes in both directions out to infinity. A segment has 2 endpoints, and then that symbol is just a line, right? It doesn't have little arrows on it. Then a ray is something that has 1 endpoint, but then the other side goes off to infinity. And of course, it could go in the other direction if we wanted to. And then that symbol is the same thing as a regular line, only it has 1 arrow on one side instead of on both. Now, even if this ray went in the other direction, the standard kind of grammar, punctuation would be this. It would still have the arrow pointing to the right. It just doesn't, it's not worth our time to come up with a completely different symbol to say, hey, the ray's going to the left, right? Because left and right are really determined by your orientation. Spin around and something that was going to the left is now going to the right. So we don't really worry about that with our symbols. Okay, the plane, right, is just that flat surface that all of these things exist in. All of these two-dimensional objects exist in this plane. Right? So think of it as like a flat sheet of paper. And so let's look at our first example. If we have this line segment, and we would call this line segment KC because that's the thing that denotes the whole length of it. And we're given that KB is 10, BM is 12, and MC is 13. It should be fairly obvious how we could compute KC by simply adding them together. And that's what we would do. So it just reminds us that line segments, you can almost think of them as the number line, right? And if you go out further and further on the number line, you're just adding up those distances as you go. So we're adding up the distances between these points. Now, of course, parallel lines are 2 lines that never touch, right? They have the exact same angle of inclination, if you want to think of it. They have the exact same slope, so they'll never intersect. Think of it like railroad tracks, right? They're next to each other, and they don't get wider, they don't get narrow, they never cross. Now I'm talking about a pair of railroad tracks. Obviously, another pair can cross that pair, but you get what I'm saying. The vertex is the endpoint of 2 line segments. So when we talk about a vertex, we're talking about where we have 2 rays coming off of the same point. And that point is the vertex of those rays. Then we can measure the angle that that vertex creates, right? And we normally label the angle by 3 points. So we put a point on each ray, and then of course we have a point for the vertex, and we call this angle ABC. We could also call it angle CBA. You can go in either direction, but you do have to go in order. You wouldn't call this angle ACB, okay? So when you see angle ABC, you always know that B is the vertex. Another definition, an acute angle is not an angle that is cute. It's an angle that is bigger than 0 but less than 90 degrees. And we say bigger than 0 because if it's a 0 angle, it's literally a straight line, right? So a straight line really isn't an angle. So an acute angle has to be more than 0 degrees. It can't be a straight line, but it has to be less than 90 degrees. And that's an acute. Then obtuse is simply the angle that is bigger than 90 but less than 180, because again, if we get down to 180, we're back to a straight line. And the way I always remember this as a student is they go alphabetical, right? Acute comes before obtuse, and so acute is the smaller one and obtuse is the bigger one. And then I think we all know that the right angle is the one that is exactly 90 degrees. It's in between those two. Okay, we know what a straight line is, right? And we now know that it has a measure of 180 degrees. We should know what adjacent angles are in order to be able to speak the same language. So in this figure here, angle BEA, right? So we start at BEA, that's the one on the left, and AED, so we start up here at AED, that's the one kind of on top. Those are adjacent angles. Two angles are adjacent if they have a common vertex and a common ray. So you can see that these two angles share the vertex E and they share the ray A. So just think of it as adjacent angles have to be next to each other, right? They have to be touching each other in the plane. Now they don't necessarily have to create a straight line, right? In this example, this angle and this angle add up to this straight line. And that we'll learn that makes them supplementary angles. But adjacent angles don't have to be supplementary. They just have to be touching. Okay, opposite angles, sometimes called vertical angles. And the reason why we use opposite instead of vertical is because vertical makes students think they have to be the vertical, right? So like this AED, this top one, and BEC, they're like, yeah, okay, those are vertical angles. But then they go, no, these aren't vertical angles. These are horizontal angles. Well, we don't call them horizontal angles. We call them all opposite angles, right? So AEB, the one on the left, DEC, the one on the right, those are opposite angles, right? AED on top, BEC on the bottom, those are also opposite angles. So the definition is you have to have two lines that intersect. And then the two angles are opposite if they are literally opposite of each other, right? They have to share a vertex, but they can't share any rays. And then that becomes opposite. Okay, complementary angles are basically adjacent angles that add up to 90. They don't necessarily have to be adjacent. So in this picture, they're adjacent, but just know that they don't have to be adjacent. So complementary angles in general are just any two angles whose angle sums add up to exactly 90 degrees. And then supplementary angles, as I mentioned before, are any two angles whose sums add up to 180. Again, they do not have to be touching. They could be two angles just floating out in space on the plane, not touching at all. But if they're two angles, if their two measurements add up to 180, they're still considered supplementary. It just so happens that when we're dealing with shapes, we're normally dealing with angles that are touching. Okay, two lines are perpendicular if they create a right angle. And to denote they're perpendicular, we use this lovely little kind of upside down T symbol because you can see that those two lines in that symbol are perpendicular, right? They create little 90-degree angles. Okay, so let's see if we can determine if the following angles are complementary or not. Well, one is 44 and one is 42. We have to remind ourselves, what's the rule for complementary? Well, they have to add up to 90. So we add those two and we see that they're 86 and they're not 90. I will remind you that, like I said, they're not touching, right? They don't have to be touching. So these things aren't complementary because they're not touching. They aren't complementary because they just don't add up to 90. Okay, how about another example? Looking for supplementary angles. So in the figure, we've got line CD, this kind of slopey one right here, that represents the road. Then we've got this angle, or sorry, this line AB, this more vertical looking one, that represents the tree trunk. And the question is, with this point of intersection of E, can we use the definitions that we saw before to show that BED, now BED is this one on the right, BED over here on the right, can we show that BED is supplementary to DEA, this one down here? All right, well, we know that supplementary angles add up to 180 degrees. We also know that a straight line is 180 degrees. So when we have this top angle and this bottom angle, and we put them together, it creates this nice little straight line. Ergo, we know that they're supplementary. Okay, given this figure, can we find angle EBD? Well, first we got to know what EBD is, right? EBD. And it's this little space right here. Well, if this is 90 degrees over here, what do we know about angle ABD? It also has to be 90 because line AC is a straight line, and that's 180 degrees. And if this is 90, then 180 minus 90 is this. And then with some simple algebra, we can figure out the missing piece, right? We know that ABE and EBD have to add up to 90. We plug in the 37 for the one that we know, subtract from both sides, and we get the missing piece is 53. It's just that easy. All right, why don't you guys take a look at this skill check. If two angles are supplementary and the measure of one of the angles is 113 degrees, find the measure of the missing angle. Go ahead and stop the video real quick and see if you can figure that one out. All right, did you get the right answer? 67? Good job. Okay, longitude and the prime meridian. So now we're going to see how some of these things relate to our planet Earth and really any orb. So longitudinal lines connect the north and south poles of the Earth and give us the positioning of east and west, right? So we can designate how far we are east and west based on what line of longitude we're on. The prime meridian is the starting point that divides the eastern and western hemispheres. We have to define it, otherwise, any of those lines could be the starting point. Latitude lines are the horizontal ones, basically, that go around the Earth, similar to where the equator is, right? The equator is the one in the middle. And those are latitudinal measures, right? So the latitudinals go around, longitudinals go up and down. So now we can kind of figure out where we are based on both of those, latitude and longitude. And those measurements are in degrees, minutes, and seconds. It's kind of crappy because there's, minutes and seconds are 60s. It'd be so much nicer if we had a measurement system that was similar to the metric system where everything was in powers of 10. But unfortunately, this system was developed a long, long time ago before the metric system, and so we're stuck with 60 minutes, 60 seconds for degrees, minutes, and seconds, right? So every degree, each 1 degree is made up of 60 minutes. Each minute is made up of 60 seconds, and then 1 second is equal to 61.6 feet. That's just the way we've divided things up. So you can think of a degree as almost like an hour, right? 60 minutes to an hour. So with that in mind, we can now convert 17.78 degrees to degrees, minutes, and seconds format, right? So instead of a decimal, right, 17.78 degrees, we can change it into 17 degrees, some amount of minutes, and some amounts of seconds. Well, what we have to do is we have to take that decimal portion of the degree measurement and convert it into those minutes and seconds, where we know from the previous slide that 60 minutes equals 1 degree. So we can hit that with a conversion, right? Because if you do 0.78 degrees times 60 minutes divided by degrees, the degrees cancel out. This is called a unit of measure conversion because we're converting our unit of measure from degrees to minutes. And then when we multiply this, our answer is in minutes. And we go, oh, we have another decimal. So we have 46 minutes, and then we got to figure out what 0.8 of a minute is in seconds. So we got to do that again. We got to convert that decimal now. So we take 0.8 minutes, and we know that there are 60 seconds in 1 minute. Again, we're doing a unit conversion, right? Because the minutes will cancel, and we'll be left in seconds, and we get 48 seconds. So 17.78 degrees is 17 degrees, 46 minutes, 48 seconds. It's just two different ways of basically describing the same measurement. You know, it's like describing something in inches and feet, or inches and centimeters, or feet and meters, right? It's just two different units of measure. How about if we want to go the other way? We want to convert something that's already in minutes and seconds and convert it back to just the decimal equivalent of our angle. Well, we have to do that with working with those minutes and seconds and converting them back with those conversions. So the easiest thing to do is to convert it all into seconds first, right? We know that this is broken up as 56 degrees, 26 minutes, 23 seconds. So we can take the 26 minutes, we can multiply it by 60 seconds, and then we can add in the 23 seconds and see that 26 minutes and 23 seconds is really the same thing as 1,583 seconds. Now that we know that, we can kind of reverse convert. We know that there are 3,600 seconds in 1 degree. Why do we know that? Because remember, 1 degree is 60 minutes, and then every minute is 60 seconds. So 60 times 60 gives us 3,600. So there's 3,600 seconds in 1 degree. You could also think about there's 3,600 seconds in 1 hour, right? If you really want to wrap your head around that. So if we take our 1,583 seconds and divide it by 3,600 seconds, that's going to give us the fraction of an hour, or in this case, the fraction of a degree. And if we stick that in our calculator and round to 2 decimal places, we get 0.44. So that means that original stuff, right, that we had, 56 degrees, 26 minutes, 23 seconds, is the same thing as 56.44 degrees. And now we've converted in both directions. Again, stop the video and see if you can convert this one. And here's your answer. All right, another example. A rocket will be launched making an angle of theta with the moon that is positioned directly overhead. Given that the rocket travels at 18,000 miles per hour and the moon completes a circular orbit of radius 240,000 miles approximately every 30 days, at what angle should the rocket be fired so that the rocket will intercept the moon? Whew, that is a lot of information to digest, right? First thing we always do with these, draw ourselves a picture so we can figure out what the heck is going on. Here's the Earth, here's the moon. They told us the moon is directly above at 240,000 meters. They also told us the rocket was coming off the Earth at some angle theta. We don't know what that is. That's what we have to solve for. And it's traveling at 18,000 miles per hour. And then we know that the moon is going to move at a certain rate, and we need these things to intersect. All right, so great. We've got our picture, and we can now kind of wrap our head around what we're trying to solve for. So let's remind ourselves that we know that distance equals rate times time. And that's going to allow us to kind of relate these things of these distances and these rates, because we also have the time of the orbit, right? We're looking for this angle. We're trying to figure out this angle. So we're basically trying to figure out, with the speed of the moon's orbit and the speed of the rocket, what angle does this have to be so that the distance that the rocket covers is going to be the same distance that the moon covers? When do they intersect? Okay, so we've got a rate of 18,000 miles per hour for the rocket, and we've got a distance of 2,400. Right? It doesn't matter in what degree we're shooting it, it's still going to be 240,000 miles away. I think I said 2,400 by a mistake. 240,000. So we know at what point, right, how long it will take for the rocket to reach the moon's orbit. Think of it as like a ring around the Earth. At what point will it hit that ring? That's an easy thing to convert. So we just take distance equals rate times time, or if you solve for time, you divide both sides by rate, and you get time equals distance over rate. We have our distance, we have our rate, and we slap it into a calculator, and we get 13 1/3 hours. I think if we were working for NASA, we wouldn't round it to 13.33. We'd go 13 1/3 hours, or 13 hours and 1/3 of an hour, right, is 20 minutes. 13 hours, 20 minutes. We'd want to be precise. But anyhow, for our math, we can do this. So we know that's how long it'll take. Okay, now let's go back and look at our picture and see what we have to do next. Okay, so we've got the time it takes to reach the orbit. Now we need to figure out basically how fast the moon is going, and we need to know it in hours, right? Everything needs to be in the same unit of measure. We had this in miles, we had this in miles per hour. We had the moon's rate in days, so we need to change that to a rate in hours. So instead of saying it goes full orbit, 360 degrees in 30 days, we're going to say it does a full orbit in 720 hours. And hopefully you're starting to see where we're going with this. Because now we figure out, all right, the degree, our measurement, right, this degree here, has to be this portion of 360. Because we basically want to know what amount of the 360, so how many degrees out of 360 does it travel in 13.33 hours out of its full 720 hours. So we're kind of setting up a simple ratio, right, of our degree over 360 degrees equals our time, right, which we want it to be the moon's time as well, all over the moon's total time. We're basically saying how far does the moon go in that many hours. All right, so we can do some math. We can cancel some things out. And then we get 2 theta equals that. So we divide it by 2. And we get roughly 6.665. I mean, it's, basically 6 2/3 degrees. And so that's the angle we would set. Fire off the rocket. And in 13.33 hours, it slams into the moon, shatters into a million pieces, and we all die. I'm kidding. Okay, how about another example? Your location is given in GPS coordinates of 32.75 north and negative, we have negatives, 79.98 degrees west. Yes, that just means that we're basically traveling, I believe it's west. So as you travel east, it's positive, and as you travel west, it's negative. As you go north of the equator, right, 32 degrees north, and then you could also say, I think it's negative degrees when you go south. I'm not a sailor, so I'm not totally positive on that, but I'm pretty sure that's how it works. But in any case, since the location has a positive value for latitude, we know that it's in the northern hemisphere. We know it's above the equator. And since the location has a negative value, right, of negative 79.98 for longitude, we can conclude that the location must be in the western hemisphere, to the west of that prime meridian. Now, note that if that negative had an absolute value greater than 1/8, so basically it was smaller than negative 180 degrees, that means you've gone halfway around at negative 180, and you're right back at the prime meridian. So if it was more than that, then you've actually gone all the way around, and you would actually be in the eastern hemisphere at that point. But at that point, instead of saying negative 200 degrees, we would just say it was positive, the difference, right? Positive 160 degrees east. So it's normally not done, right? Think of it that way. Okay, so we have this thing called a longitudinal adjustment factor, and it's used to find the distance between lines of longitude at a certain latitude measure. Because, if you remember from the picture, lines of longitude are not parallel. Lines of latitude are. Here is the picture, right? Latitude, you can see they're all concentric circles. They're all parallel. They never touch. But longitude, see how they all meet at the North Pole, and they also meet down here at the South Pole, and you can kind of see they're wider at the equator, and they get closer and closer and closer together as you go north and south of the equator. So we have to have some sort of formula for figuring out how far apart these lines actually are, so that when we're giving our position in terms of longitude and latitude, we can actually calculate distances. And that adjustment factor is given by this funky little formula. It's not that bad, right? So the LAF, the longitude adjustment factor, is simply 69 minus 4 times the latitude measure divided by 10. Remember, latitude is just where you are north and south. For example, if Amanda starts at a GPS location of 32.7 degrees north and negative 79.9 degrees west, how far in miles is Amanda away from her destination of 35.15 degrees north and negative 90.06 degrees west? Now, what do we always do when we're trying to figure out geometric questions? We always want to draw ourselves a picture. And because we're dealing with distances, with north and south and east and west distances and then connecting the points, it should seem fairly obvious that we want to create a right triangle and use good old Pythagorean theorem to help us find those distances. So here's the picture. Here's her starting point. Here's her finishing point, right? So she started at 32.75 north. She went up, right, to 35.15. So this point here would be at a latitude of 35.15, and then she went from this point of negative 7998 to further west, right, to further negative 90.06. So we can now calculate these distances just based on the differences between these 2 points. The first thing we want to do is find the lengths of the legs of the triangle. And we can see from our picture that we can figure out this vertical length from the starting point to this point P as simply the difference between the two northern measures, right? The two longitudinal measures. Sorry, the two latitudinal measures, which are the ones that go around like the equator. So we're doing the difference between, you can think of these almost as like the difference between, they should be the y degrees, but they're listed first, right? So 35.15 and 32.75. So the difference between kind of this height and this height is 2.4 degrees. And then we can convert that into miles because we're told that there are 69 miles in each degree on the globe, right? As you go 1 degree north from the equator, you've traveled a distance of 69 miles. So going from 32.75 up to 35.15, that line of latitude, that represents traveling 165.6 miles. Great, easy, simple. We can also figure out the change in longitude, right? These vertical longitudinal lines. And the change between these two is the change between the negative 79.98 and the negative 90.06. Since they're both negative, we can just think of looking at the difference between their absolute values, right? And so it's 90 minus 79, we get 10.08. So you can think of this leg of the triangle as being basically 10.08 degrees, this one being 165.6 miles. We can't convert this into miles yet. We got to use that fancy formula first. So we use our lovely LAF formula. We plug in what we know, our latitude measurement, right? We're up here at a latitude of 35.15. We divide that by 10. We multiply it by 4. We subtract that from 69. And that tells us that each line of longitude is roughly 55 miles apart. And that means 1 degree. If you move 1 degree, you've gone 55 miles, roughly. So we can take that and go, okay, well, they're not 1 degree apart. They're 10.08 degrees apart. So we're going to multiply that by we can go ahead and round to 55. And we get that the total distance is roughly 554.4. So now we have that horizontal distance, we have that vertical distance. We can use Pythagoras' theorem, right, where we square this one, add them together, take the square root, and gives us that one. Right, so here's all that work. Square, 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 square. Take a square root, and bingo, bango, bongo, we're basically 578.6, right? Right around 579 miles apart. That's the distance traveled. I know that felt like a long one, but it really was just a multi-step process. It wasn't too bad if you take it step by step. Okay. Next, let's remind ourselves of the good old SOHCAHTOA. If you've ever heard SOHCAHTOA before, right? SOHCAHTOA is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So SOHCAHTOA. It's just a way to kind of remember those relationships. However you want to memorize it. I always remembered that cosine kind of sounds like cousin, and your cousins are related to you, so they're adjacent to you. So I remembered that cosine was adjacent over hypotenuse, which made me remember, oh, then sine has to be the other one, so it's the opposite over hypotenuse. And then your tangent is, if you remember anything about trig, you know that tangent is sine over cosine, so it's opposite over adjacent. So there's a bunch of different ways you can kind of help yourself remember those relationships. Once we know that, we can use that to solve for missing pieces in right triangles. So for instance, Sam is building a deck on the back of his house. The deck is 4 feet off the ground. According to the building code, the maximum angle for the incline of the steps for the deck is 30 degrees, and the maximum length of the step incline can be 8 feet. So what that basically means is it's going to tell you how far out you can start your steps, and then that'll help you build it, right? So we draw ourselves a little picture. We know that we have this 4-foot vertical drop. We know that the total slant length, right, the maximum length of the step incline is 8 feet. The angle of inclination, right, is 30 degrees, and then that will give us the distance to the first step. All right, so now we're just going to figure out which one we need to use. Well, since we have this angle and its opposite measurement and its hypotenuse measurement, that's sine, because sine relates opposite over hypotenuse. So we plug in what we know. We've got the degrees, we've got the opposite and the hypotenuse, right? We get 1/2, and we can see that sine of 30 is actually 1/2. You put sine of 30 in your calculator, you'll get 1/2. Okay, great. So we verified that everything works, but that doesn't help us. We want to know what this measurement is here, right? So if we're using the 30-degree angle, this measurement is adjacent to us. So we could either do cosine and have adjacent over hypotenuse, or we could do tangent, because tangent gives us opposite over adjacent. We just use either one because it will help us solve for the missing piece. Let's go ahead and use cosine. Cosine of 30 is adjacent over hypotenuse, which is the x that we're looking for, over the 8. Multiply both sides by 8, right? So we can solve for x. Plug this into our scientific calculators, and we get that x equals 6.93 feet. Now make sure when you plug this in your calculator, you have to be in degree mode, because you're putting in 30 as a degree. If you're in radians mode, it's going to give you a totally wrong answer. Now, we also could have done it with tangent, right? As I mentioned, tangent of 30 is opposite over adjacent. So we set it up as 4 over x. Now to clear the fraction, we multiply both sides by x. And then to solve for x, we have to divide both sides by tangent of 30. You can see that it's an extra step. They both work, but cosine gets us there a little faster. But that's okay. Doesn't matter. They both give us 6.93, right? 6.93, 6.93. And it should work that way. Okay, how about a skill check? Let's see if you can use the Pythagorean theorem and the result from example 10 to confirm that the side lengths form a right triangle. So stop here and give that a try. Okay, well, here's your answer, right? We know that 4 squared plus b squared has to equal 8 squared. B squared has to equal 48. We get that by taking 8 squared and subtracting 4 squared from it. Take the square root of 48 and we get 6.928, which is 6.93, which is the same thing. Yay, we did it right. Okay, how about one last example? Well, maybe two. Yeah, we'll do two. A hiker knows that the distance from a point A on a map to another point B is 7 miles apart. She began at point A and headed west until she was due south of point B, and is now at point C. She needs to determine her distance from both point A and point B, given that the heading of her route from point A was at a 46-degree angle from the line between points A and point B, as shown in the figure. I know this is making your head swim, but once I show you the figure, it'll make more sense. When she arrives at point B, she also needs to know what angle she will need to make with her due north route to return directly to point A. So here's basically what happened, right? So let's bring it back and look at the words. Okay, so she knows that the distance from A to B is 7 miles, right? The straight distance. She started at A, and headed due west, right? So that's why we've got this line here. Until she gets to point C, which is directly south of B. Now, she needs to determine her distance from both point A. She needs to figure out how far she traveled to get to C. And then, given that she started at a degree of 46 degrees, right? So she was 46 degrees off from B. That's this angle here. She needs to figure out then how far it's going to take her to get back to B, and then what angle measurement, right, what degree measurement is going to get her back on a heading so that she could travel straight back to A. Okay, so that's what's happening here. We need to figure out this distance, and then this angle. I think all of you are thinking this angle is pretty easy, but we'll save that for last. Okay, first things first. We need to find the length of sides A and B and the measure of angle B in the figure. And we know that sine of A, right? We know if we take the sine of this angle, it's going to equal A over 7. Just like if we took cosine of this angle, it's going to equal B over 7. So we could use both of those to solve for those two things. So we set it up, right? Sine of 46 equals A over 7. To solve for A, we multiply both sides by 7. We get this. We stick it in our calculator. We get 5.04. So A is roughly 5.04. Then we move on. We could use Pythagoras' theorem to solve for B, or like I said, we could do the cosine of 46 and solve it that way. But either way, we get that B is roughly 4.86. Now, the last thing we need to figure out is the angle, but like I said, that's pretty easy because we know that any triangle, the sum of the interior angles is always 180 degrees. We know that this was a 90-degree angle because they said that she went, due west, and then she's going to go due north, so that's going to create a 90-degree angle. So all we have to do is take 180, subtract the 90, subtract the 46 to get the leftover, which is 44. So now we know everything. She traveled 4.86 miles west. Then she would need to walk 5.04 miles due north to get to B. And after that, she can turn 44 degrees from south to get to this line, and then walk the 7 miles back to A. Okay, one last example. A ship's sonar locates a shipwreck at 17 degrees angle of depression. A diver is lowered 105 meters to the ocean floor. How far does the diver need to travel along the ocean floor to get to the wreckage? So this 17 angle of depression just means from the horizontal, it's 17 angles down. Depression is down versus inclination, which would be 70 degrees up. So like always, first thing we do is make a sketch so we can figure out what's going on. Right? 105 meters straight down, we want to find this distance. We know this angle is 17. If we're going to deal with a right triangle, we know we've got a right angle here. We need to know some interior angles. But, what do we know about these two angles? Right? We know that the red line and the horizontal line create a 90-degree angle. So these two angles have to add up to 90, which are called what? That's right, complementary. So to find this one, all we simply do is subtract 17 from 90 to get that angle. So that's the first thing we're going to want to do. So we do that, and then we can start working on finding distances. And we could do those with, sine, cosine, tangent, all sorts of different things. But we could also notice that because these are parallel lines, and this line intersects it, these become opposite interior angles, and this is 17 degrees. Or, right, if you did the math and calculated what this angle was, which, it's 90 minus 17, which would be 73. Then we know this all adds up to 180, right? And this is a 90, this is a 73, and lo and behold, this is back to 17, right? So it kind of proves that opposite interior angles are the same. And then from that, we could use this as our reference angle and figure out this distance is tangent opposite over this. You could have used this angle too. The book just likes to always use the angle on the horizontal, but you could do this one. If you did this one and you want to find D, you could use tangent, and tangent would be D over 105. And in my That's one less step because we don't have to do kind of a double multiplication, right? Because to solve for d, we got to multiply both sides by d to get it out of the fraction. Then we got to divide both sides by tangent of 17 to get d all by itself. Then we can finally do the math and get 343.44. So they have to walk approximately 343 meters. That's a big old walk. It'd be nicer if the boat would get a little bit closer. All right, that's our last example, and that's all I've got for you for today.